When we left off last time, like before spring break, we had talked a little bit about bounded functions, and we had a problem, I think within a slope field problem, where the function eventually began to approach some limit. There was a horizontal asymptote. And I mentioned that there was something more to come on this, and it's odd enough that we're starting after this whole virus thing with differential equation models that model how viruses are spread. So look, there's a tie into the whole thing. So I put a little set of notes up here that I didn't feel like writing all out by hand about modeling with differential equations. Exponential growth assumes that exponential growth goes on forever. So if you say that something is always doubling, something is always 2 times what it was before, and that exponential growth function just keeps going and going, usually long beyond what we can see on a graph. But that's realistic for a small period of time, but it's not usually realistic forever. So something that's more realistic is what we call logistic growth. So here's the definition of logistic growth. Suppose some quantity is increasing at a rate, and you notice that I made an emphasis on the rate. So it's a rate that is jointly proportional to its size and the difference between some fixed positive number m. Sometimes it's called the maximum population, sometimes it's called the carrying capacity. So it's the difference between that and the size of its population. So the logistic differential equation looks something like this. Because it's a rate of growth, it's going to be a rate in the change of population over time. So we said it's jointly proportional. So there's some proportionality constant. We'll call it k over m. And then the two things are the current population and the difference between the carrying capacity and the current population. So what that means is that when this value here is very large, that's when it'll grow the fastest. So when the current population is 2, but the carrying capacity is 10 million, then it's going to increase very quickly because that difference is very large. On the other hand, when that difference is very small, in other words, if the carrying capacity is 1,000 and the current population is 998, then there's not going to be a very large growth because you're almost at that carrying capacity. Now, think of that in terms of the spread of infectious disease. The carrying capacity is basically the entire population or the entire population that will at some point get infected. When it first starts, right, when the disease begins to first spread, it's going to start with that very first person. Right? So you're going to start with a very small value down here. And then, assuming there's no isolation or anything, that rate of infectious spread is going to increase very quickly. You're going to sneeze on somebody, and then they're going to sneeze on 2 other people, and they're going to sneeze on 2 other people, or 3 other people, or 5 other people, and you see how very quickly that's going to increase. Well, what's going to happen, strangely enough, is that after a while, you're going to run out of people to infect. And so you're going to start sneezing on people that are already infected with it, and is going to start to level off. That's what a logistic growth curve looks like. So it starts off very small, and then right in the middle here, it increases very quickly. When that difference between the current population and the carrying capacity is very large, it increases quickly. When it begins to level off is when that difference gets very small. So we could, if we wanted to, start every problem as a differential equation and work our way backwards. But because this is an honors course, we probably don't want to do that. We probably want to figure out how to come up with a formula that could help us to solve this differential equation as a function in population at a certain time. So I want to find out the population at time 0 and at time 1 and at time 2. I want to find out how long it's going to take before half the population is infected, before 95% of the population is infected, and so forth. So let's start by separating my differential equation. So I want to solve this for P in terms of t. I want a population at any time t. So the first thing I'll do is I'll separate my variables. I'll put everything that has a p on the left side and everything that does not have a p on the right side. So I'm going to put dp over what? I divide both sides by p. I divide both sides by m minus p. On the other side, I've got a k over m, and I've got a dt. All right. My issue now is I have to do something with this left-hand side, because eventually I want to integrate both sides, but I can't quite integrate both sides unless I do something with that left-hand side. So let's work now as sort of a sidebar to split up 1 over p times m minus p. Now, in order to do that, we're going to need partial fractions. We're going to need something over p plus something over m minus p, and very quickly we realize that we don't have numbers on the right-hand side anymore. So the idea of setting up a system and solving is a little bit more difficult because we don't have any numbers to set them equal to, and so now we have extra variables. Let's multiply both sides through. I get 1 equals a times m minus p plus b times p. Okay, and so I'm going to use that little trick that I used back when we did partial fractions the first time around, which is the first thing I'm going to do is I'm going to let p equal 0. If p equals 0, that wipes out that second piece, and I end up with just 1 equals a times m, and a is 1 over m. All right, let's pick another one. Let's say I let p equal m. Well, if p equals m, that first piece here goes away, and I understand it's kind of boring. I end up with a b times m, and so b is also 1 over m. So I can split this really as 1 over m times 1 over p plus 1 over m minus p. Okay, so this on the left-hand side is going to be replaced by that. Ugh. All right. Let's slide this up and keep going. So we said the left-hand side became 1 over m times 1 over p plus 1 over m minus p. The right-hand side became k over m dt. Well, right away, let's multiply both sides by m. Right, so we'll multiply that side by m, we'll multiply that side by m, and I end up with 1 over p plus 1 over m minus p equals k dt. Okay? Now we integrate both sides. I lost my differential on the left-hand side. That differential on the left-hand side should be a dp. Okay, so I'm going to integrate this whole side with respect to p, that whole side with respect to t. So on this side, integrate 1 over p with respect to p, and I get the natural log of p. I'm going to leave out my absolute values because my population is not going to be negative. Over here, if I integrate that second piece, I'll end up with the natural log of m minus p, but there's also a negative that pops out of it, because when you integrate this, and the variable of integration is p, then that negative before the p means you're going to have to divide by -1. I'll think of it as multiplying by -1. Okay, on the right-hand side, when you integrate that k with respect to t, you just end up with kt. Now, technically, there's also constants of integration that pop up here, right? There's a constant of integration on this side. Let's say there's a constant of integration that pops up on that side. But it really doesn't matter that I have two separate constants of integration. Why not move them all together to the same side? So I'm going to say I got the natural log of p minus the natural log of m minus p plus, now, here comes a little bit of hand-waving creativity. Suppose I take those two constants of integration and I subtract them, right? So I've got c sub 2 minus c sub 1. I'm going to rename this the natural log of a, where a is a constant. And I'm doing that for no other reason than convenience. Because if I call the constant the natural log of a, it turns out it makes things a whole lot easier in my life as I keep going. All right, so now it looks like there's no constant of integration on the right-hand side, but that's simply because I moved them over to the other side and combined them into a natural log. What does this mean? That means the entire left-hand side can be combined into one natural log. The a and the p go on top because they're the ones with plus signs. The m minus p goes on the bottom because that was the one with the minus sign. And I end up with a kt on the other side. And now the fun begins. If it hasn't already begun, now it begins. My goal, of course, is to solve for p, which is buried inside a natural log and on the top and the bottom of a fraction. So the first thing is let's do an e to both sides to break that out of the natural log. So I end up with ap over m minus p equals e to the kt. All right, so now I'd like to work my way back again towards those p's. So the first thing I'm going to do is I'm going to flip this thing. So when I flip, the left-hand side becomes m minus p over ap. The right side, instead of writing a 1 over, I'm just going to do an e to the negative kt. Okay, push this up. Multiply both sides by a. So I multiply this side by a, and I multiply that side by a, and I end up with m minus p over p equals a e to the negative kt. Now you realize that a that's in there is actually part of my constant of integration. Right? So if it looks like there's no plus a c at the end, oh, there is. It's that a that's over there. All right, this is good, because now I can separate this into an m over p minus 1. Right-hand side stays the same. Move that 1 over, and I get m over p equals 1 plus ae to the negative kt. Let's flip again. So when I flip now, I end up with p over m equals, and this time I actually will put that in the bottom of a fraction, 1 plus ae to the negative kt. And the only thing I'm left to do is multiply both sides by m. So I get this formula, p equals m over 1 plus ae to the negative kt. This is a differential equation that's been solved now for a logistic growth curve. So this is a logistic growth function. Now your textbook may do this a little bit differently. I like this version of it because that m that was in the original differential equation is the same m that's up on the top there. And the k that was in your original differential equation is the same k that's over here. All right, so we took something that was in differential equation form and we solved for it. And yeah, it was kind of a messy process, but you realize that everything we've done is something that you already know how to do, right? I didn't teach any new techniques that you didn't already know. All of these things you already knew. All right, so I'm going to make a part 2 of this where we take this logistic growth function and we actually solve a problem with it. All right, so part 2 on the way.